And here we have our last example in our module, or our last set of examples in our Module 6.2 class notes. Another video where we are solving logarithmic equations with examples 9 through 11. And I've chosen to work example 10 first because example 10 is very similar to the examples that came in our last video. So it's another good example of that same kind of process. And then we'll see in examples 9 and 11, not a harder process, but a slightly different process that we need to see how to work with a slightly different type of logarithmic equation. This one, example 10, has us solving 2 times log of 8n plus 4 plus 6 equals 10. And the goal is to solve for n, get the variable by itself. There's a few steps that we can take right off the bat. I can subtract 6 on both sides. 6 from 10 leaves me with 4, so I've got 2 times log of 8n plus 4 equals 4. Again, there's a step that I can take, a simple algebra step, divide both sides by 2. 4 divided by 2 is 2, so I've got log of 8n plus 4 equals 2. And now on the left-hand side, I'm stuck with the logarithm. But that's where the definition of a logarithm comes in. Same definition we've been using all module, and even the last module when we introduced logarithms in module 5. We've been applying this definition of a logarithm and leveraging this definition of a logarithm the whole time. Why stop now? Here we've got log base 10 of the result 8n plus 4 equals the power 2. Let's rearrange that to exponential form with base 10 to the power 2 equals the result 8n plus 4. Having done that, now it's not too difficult to solve for n, get n by itself. Of course, 10 squared, 10 times 10 is 100. And then let's subtract 4 on both sides. And then divide by 8. And we get n equals 12. Now, as we saw in the last video for examples 7 and 8, we saw and we now realize that with a logarithmic equation, we always have to check. In fact, it's a good idea to check any equation, but it's necessary to check for extraneous answers in a logarithmic equation. So let's check. Let's plug 12 in for n in our equation. 2 times log of 8 times 12 plus 4 plus 6 equals 10. And let's work through the math, starting with inside the parentheses. Inside the parentheses, I've got 8 times 12 is 96. And then 96 plus 4 is 100. And now I've got the log of 100. That's log base 10 of 100. That's what power do I raise 10 to get 100? 10 to the second power is 100. So log base 10 of 100 is 2. And then I've got 2 times 2 plus 6. That's 4 plus 6 equals 10. Sure, that works. That checks out. So we're good there. So now we can conclude that we have one answer, n equals 12, that works, and no extraneous solutions. All right. Now, question number 9, example number 9, is another logarithmic equation. In principle, really no different, but a difference here, to be fair, is that now we've got 2 logarithms. We've got a logarithm on both sides of the equation. That's a bit of a difference. We don't have just a logarithm equal to a number. We've got a logarithm equal to a logarithm. And that's not necessarily difficult. So let's keep our brains straight here as we consider. Actually, if you think back to the exponential examples that we started with, examples 1 through 3, way back at the beginning of this module 6.2, we had exponential equations where both sides were powers of the same number. And that wasn't terribly difficult. Here we have logarithmic equations where both sides are logarithms of the same base. Similarly, this isn't terribly difficult because we have another one-to-one property. We've got a one-to-one property of logarithms that says if you've got two logarithms equal to each other, same base. I won't trick you with different bases of logarithms. Don't worry about that. But if you have two logarithms, same base, equal to each other, well, if they're equal, then they must be the same number. It's really as simple as that. If I've got two logarithms equal to each other, they're the same number, then the arguments, what's the numbers inside the parentheses, have to be the same number. For them to be equal to each other, yeah, they have to be the same number. That's the one-to-one property of logarithms. And we can apply that here in question number 9 to say if I have log base 7 of x plus 12 equals log base 7 of 12x, if they're equal to each other and they're both log base 7s, well then x plus 12 and 12x must be the same number. X plus 12 is equal to 12x. So in that way, using that one-to-one property of logarithms, I can effectively cancel the log on both sides of the equation. And now I've got x plus 12 equals 12x. And I can solve that. Subtracting x from both sides, dividing both sides by 11, I get x equals 12 over 11. This is a logarithmic equation we need to check. Let's check and plug 12 over 11 in for x on both sides of that equation. Log base 7 of 12 over 11 plus 12 equals log base 7 of 12 times 12 over 11. And now you got to remember how to add fractions. You got to remember how to multiply fractions. Adding fractions means you need to find a common denominator. On the right-hand side, multiplying fractions is just multiplying. 12 times 12 is 144 over 11. On the left-hand side, changing to a common denominator and then adding gives me log base 7 of 144 over 11, which is the same thing I got on the right-hand side. If you're stumbling on those fractions, ask. We've reviewed how to add, subtract, multiply, and divide fractions, but if you're still stumbling on those fractions, ask. Ask me. Ask the tutors in the tutoring lab, ask the tutors in our dedicated tutoring sessions that we have every week. Come and ask, please, we'll be happy to answer. But as we see here, done correctly, the fractions are equal, the logarithms are equal on both sides of the equation, so we're good. And we found a solution of x equals 12 over 11, and it worked, and there's no extraneous solutions, so we're done there. Last example, example 11, we've got logarithms equal to logarithms, and it's going to be pretty much the same story here, except of course every example has a bit of a twist because, because we made it a whole nother example. There's a reason I'm asking you this one on top of the ones that we've worked previously. And here we see the difference is we've got not just a single logarithm equal to a single logarithm, but we've got two logarithms on the left-hand side. We've got the natural log of x minus 2 minus the natural log of x equals the natural log of 54. And our one-to-one property that talks about a logarithm equal to a logarithm only works if you've got a single logarithm equal to a single logarithm, not a difference of two logarithms like this. But you remember what we can do with a difference of two logarithms, how we can combine those using our quotient rule into a single logarithm of a quotient. The natural log of x minus 2 divided by x. That's our quotient rule for logarithms back from module 6.1. And now we've got a single logarithm equal to a single logarithm. Now we can strip away the logarithms and say we must have x minus 2 over x equal to 54. And we don't like fractions. I get that. That's okay. Get rid of the fractions. Multiply both sides by x. So that you've got x minus 2 on the left-hand side equals 54x. Now subtract x and divide by 53, and you get x equals negative 2 over 53. Now we need to check that answer. Plug negative 2 over 53 in for x. So we've got the natural log of negative 2 over 53 minus 2 minus the natural log of negative 2 over 53 equals the natural log of 54, and we want to check to see does that work. And no, it doesn't, because we've got the natural log of a negative number, and we can't take the log of a negative number. So x equals negative 2 over 53 doesn't work. It's an extraneous answer, and it was our only answer. So we conclude that there is no solution to this equation. We found an extraneous answer, but that's not a solution. And this is how we would note our answer in this case.